Now we're going to move on to a completely new kind of function called the quadratic function. The simplest quadratic function is y equals x squared and has this parabolic shape. For positive values of x, we get faster growth for larger values of x, but the accelerating growth is not as extreme as we would expect for an exponential function. Squaring a negative value of x also produces a positive value of y, so we see a mirror image of the positive x values in the negative x values. In addition to generally changing less rapidly than the exponential function, a quadratic function is able to take on the value y equals 0, which no exponential function is capable of. Also notice that the quadratic function is capable of decreasing and increasing in the same function. If we start far to the left of the graph, we see a decreasing behavior until we reach x equals 0, and then it begins increasing. In fact, every function we've seen so far has to either decrease or increase. A quadratic function is the first function that's able to demonstrate both behaviors. Of course, there are more complicated quadratic functions than that. We can obtain them by thinking of the most basic quadratic function and then applying the transformations we saw in the previous section. From the graph, it appears that this quadratic function was obtained by beginning with the basic function, flipping it vertically, shifting to the right by 2, and then shifting up by 3. Above the graph, I have two expressions that both describe this graph. The first form has some advantages that we'll make use of later in this chapter, but it's not good for seeing how the graph was transformed. If I compare the second form to the base graph y equals x squared, I can see all the transformations. The x minus 2 that's occurring inside the square tells me a horizontal shift to the right by 2. The negative that's in front of the square indicates the vertical flip, and then the plus 3 after all of that indicates the vertical shift up by 3. These two forms are called the general form and the standard form, respectively. The general form is usually written ax squared plus bx plus c. A, b, and c are just numbers called coefficients, and we only require that a is not 0 because otherwise the x squared term vanishes and we no longer have that parabolic shape. B and c, however, could be 0, as we saw with the example y equals x squared. The standard form is sometimes called the vertex form because I can more clearly see the transformations that have taken place. The x minus h tells me that a horizontal shift has taken place, and the plus k tells me that a vertical shift has taken place. And depending on the signs of these numbers will tell me the direction of these changes. The value of a in front could indicate flipping or stretching depending on the value. If I begin with the standard form and wanted to convert to general form, it means that I should expand the square and then combine all the like terms. The definition of x plus 3 squared is x plus 3 times itself. So I write that out to emphasize that the result is not x squared plus 9, but rather we have to multiply each term in the left parentheses by each term in the right parentheses. If I begin with the first x in the left parentheses and then multiply it by everything in the right parentheses, I have x times x and x times 3, and I end up with x squared plus 3x. Then if I move to the 3 in the left parentheses, I multiply that 3 by x and 3 by 3 to get another 3x plus 9. Finally, combining all the like terms, I have the x squared plus 6x plus 7 general form. What if I began with the general form and wish to convert it to standard form in order to see how the graph has been transformed? We accomplish this with a technique called completing the square. Disregard the plus 7 for a moment and ask, what number would I like to have there so that x squared plus 6x plus that number is a perfect square? Trust me for a moment that this number is plus 9. So I'd like to add plus 9, which I've done in green, but I also have to subtract plus 9, because if I simply add plus 9 to this function, then I've changed the meaning of the function. But adding and subtracting the same number has no effect on the function. But writing it in this way will let me do some manipulation. The x squared plus 6x plus 9 factors into the perfect square x plus 3 squared. The green plus 9 has become the green plus 3 after factoring. The blue minus 9 and the plus 7 that we began with were uninvolved in that factoring. Now I can combine those like terms, and I have the standard form x plus 3 squared minus 2. How did I come up with the plus 9 in the first place? I took the coefficient 6, divided by 2 to get 3, and squared to get 9. Why does this work? Recall when we multiplied out x plus 3 squared, we got a copy of 3x and another copy of 3x. So those two 3x's need to add up to 6x, which is why I started by dividing the 6 by 2. If we were to multiply those parentheses out, the new number we've added is 3 times 3, or plus 9, which is why I squared. In examples where the coefficient a is equal to 1, then choosing b divided by 2, all squared, will always work. Now that we have the standard form, we can visualize the graph. This expression tells me that I should begin with the base graph y equals x squared, shift to the left by 3, and then shift down by 2. Since there's no negative sign in front, I know that the graph should open upward just as the base graph does. So the result is I have an upward opening parabola whose vertex is -3 and -2.